Download this code from codegive.com, link in the description below. OK, let's dive into processing OpenStreetMap, OSM, data into vector tiles using Dane Springmeyer's tools and techniques. This is a multi-stage process that requires some understanding of data formats, databases, and command line utilities. I'll break it down with detailed explanations and code examples. High-level overview. The general workflow is as follows. 1. Obtain OpenStreetMap data *, get the OSM data for your area of interest. 2. Import into postgis *, load the OSM data into a PostgreSQL database with the postgis extension. 3. Prepare the data *, clean, simplify, and optimize the data for vector tile generation. This involves writing SQL queries. 4. Create vector tile queries *, define SQL queries that extract the data for each vector tile layer. 5. Generate vector tiles *, use tools like tilemaker, tippecanoe, or pg_tileserve to generate the actual vector tiles from the SQL queries. 6. Serve the tiles *, set up a tile server to serve the vector tiles to your mapping application. Step 1. Obtaining OpenStreetMap data. You have a few options for getting OSM data. Overpass API * use the Overpass API for small areas. This is good for quick tests or small regions. Planet.osm * download the entire planet's OSM data, very large, tens of gigabytes. Geofabric downloads * download precut OSM data for specific countries or regions from https://download.geofabric.de/ https://download.geofabric.de. This is often the most practical option. *bbike extracts * create custom extracts of any area from https://extract.bbike.org/ https://extract.bbbike.org. Good for custom areas. For this tutorial, let's assume you've downloaded a geofabric extract, such as germanylatest.osm.pbf. This is a protocol buffer binary format, PBF, file, which is a compressed and efficient format for OSM data. Step 2. Importing into PostGIS. PostGIS is a spatial database extension for PostgresQL. You'll need PostgresQL and PostGIS installed on your system. The installation process varies depending on your operating system. Here's a brief guide. *Ubuntu/Debian *. Mac OS, using Homebrew. *Windows *. Download an installer from the Enterprise DB website, https://www.enterpriseid.com/download/postgresql downloads, https://www.enterprise.b.com/download/postgres-postgresql-downloads. Creating the database *. 1. Open a terminal or command prompt. 2. Create a PostgreSQL user, optional, but recommended for security. 3. Create a PostgreSQL database. 4. Connect to the database and enable PostGIS. Inside the PSQL prompt. Importing the data *. We'll use OSM2PGSQL to import the OSM data into PostGIS. Install OSM2PGSQL. *Ubuntu/Debian *. Mac OS, using Homebrew. Now, run OSM2PGSQL. Explanation of options. *D OSM_data, database name. *U OSM_user, PostgreSQL user. *H localhost, host, usually localhost. *W, prompt for password. *S, do not create an index, we'll create them later. *s default.style, use the default style file, defines how OSM features are mapped to database tables. *Germany latest.osm.pbf, the OSM PBF file. Important, you may need to adjust the H and U parameters to match your PostgreSQL setup. Also, the default.style file is usually located in /usr/share/osm2pgsql/default.style or similar depending on your system. You might need to copy it to your working directory or specify the full path. osm2pgsql provides a command to print the default style file path. Try running osm2pgsql print default style to locate it. Step 3. Preparing the data. After importing, you'll have three main tables. *planet_osm_point, points, example shops, amenities. *planet_osm_line, lines, example roads, rivers. *planet_osm_polygon, polygons, example buildings, langes. *planet_osm_roads, special table for roads. Now, we need to prepare the data for vector tiles. This includes adding an osm_id column. If missing older versions of osm2pgsql might not automatically add an osm_id column. Add it if necessary. It's crucial for identifying features. Creating indexes. Indexes speed up spatial queries. Simplifying geometries. Vector tiles have size limits. Simplify the geometries to reduce the data size. Use st_simplify preserve a topology to maintain topology, avoid gaps. This is a crucial step. Skipping it will result in very large tile sizes and poor performance. Example. Repeat for planet_osm_point, planet_osm_polygon, and planet_osm_roads. Experiment with the tolerance value, example 1, 5, 10, 20, based on your needs and the zoom levels you plan to support. Larger tolerance values mean more simplification and smaller tile sizes, but also more loss of detail. Filtering and tagging. Create views to easily query the data, for example roads. Step 4, create vector tile queries. Now comes the core part, defining the SQL queries that will be used to generate the vector tiles. These queries extract the data for each layer in your vector tiles. Here's a basic example for a roads layer. Explanation. *get_roads, z integer, x integer, y integer. This is a PostgreSQL function that takes the zoom level, z, tile x coordinate, x, and tile y coordinate, y, as input. *st_tile_envelope, z, x, y, generates a bounding box geometry for the tile at the given zoom level and coordinates. This bounding box is in WebMercator, EPSG 3857. *st_transform, geometry, SRID, transforms the geometry to the specified spatial reference identifier, SRID. We transform from the OSM data's SRID, usually 4326, WGS84, to WebMercator, 3857, for vector tiles. *st_asmtgeom, this is the critical function. It converts the geometry to a vector tile geometry. *st_transform, geometry, 3857, the geometry transformed to WebMercator. *st_tile_envelope, z, x, y, the tile boundary box. *4096, the tile extent, the size of the tile in pixel coordinates. *0, buffer around the tile. *false, clip geometries to the tile boundary. *st_intersects, geometry, st_transform, st_tileenvelope, z, x, y, 4326, filter the data to only include features that intersect the tile boundary. Important, the tile envelope is in Web Mercator 3857, so we transform it back to WGS84 4326 to compare it with the geometry column. *st_asmv, roads, encodes the query result into a mapbox vector tile, MVT, format. The second argument is the layer name. *parallel safe allows the function to be executed in parallel, which can significantly speed up tile generation. This requires PostgreSQL 9.6 or later. Important considerations for queries **** zoom levels ** you'll likely need different queries for different zoom levels. For example, you might include more detailed features at higher zoom levels and simplify features at lower zoom levels. You can use case statements in your SQL queries to handle this. *layer names * each query should produce data for a single layer in your vector tiles. Choose descriptive layer names, example roads, buildings, water. *data types * vector tiles support specific data types, string, integer, float, boolean. Cast your data to the appropriate types in the queries. *attribution * consider including attribution information in your vector tile data. Example queries for other layers *. Here are some example queries for other layers, adapt them to your specific data. *buildings * water areas *. Step 5, generating vector tiles. Now that you have the SQL queries, you can use tools to generate the vector tiles. Here are a few options. *pg_tileserve *, recommended for ease of use and direct serving. pg_tileserve is a lightweight tile server that directly serves vector tiles from your PostGIS database using the SQL functions you created. One installation * follow the instructions at https://github.com/crunchydata/pg_tileserve, https://github.com/crunchydata/pg_tileserve. It usually involves compiling from source or using a pre-built binary. 2. Configuration * pg_tileserve requires a connection string to your PostgreSQL database. You can set it using the database_URL environment variable. 3. Running the server *. 4. Accessing the tiles * by default, pg_tileserve runs on port 7800. You can access the vector tiles using URLs like this. pg_tileserve also provides a built-in viewer at http://localhost 7800/. *tilemaker *, flexible, but more complex. Tilemaker is a powerful tool for converting OSM data to vector tiles. It uses a configuration file to define the data sources, layers, and styles. It's more complex to set up than pg_tileserve, but it offers more flexibility. One installation * follow the instructions at https://github.com/system/tilemaker, https://github.com/system/tilemaker. 2. Configuration * you'll need to create a process.lua file that defines the tile generation process. This file specifies the database connection, SQL queries, and layer configurations. See the tilemaker documentation for examples. 3. Running tilemaker *. This will generate vector tiles in the tiles directory. *tippecanoe*, for pre-generating tiles from GeoJSON. Tippecanoe is excellent for pre-generating vector tiles from GeoJSON data. It's not directly connected to postgis. You would first export data from postgis to GeoJSON and then use Tippecanoe to create tiles. This is a good option if you want to create static tile sets. 1. Installation *. Follow the instructions at https://github.com/mapbox/tippecanoe, https://github.com/mapbox/tippecanoe. 2. Exporting GeoJSON * use ogre to export data from postgis to GeoJSON. 3. Generating tiles with Tippecanoe *. This will create an MB tiles file, tiles.ntils, containing the vector tiles. Step 6. Serving the tiles. Once you have generated the vector tiles, you need to serve them to your mapping application. *pg_tileserve*. As mentioned before, pg_tileserve already is a tile server. You can use it directly. *MB tiles server*. If you use Tippecanoe, you can use a simple MB tiles server like tileservergl. Install it with npm install gtileservergl. Then, run tileservergl tiles.ntils. *static tile server*. If you have a directory of individual vector tile files, example generated by tilemaker, you can use a static file server like Nginx or Apache. Just configure the server to serve the tiles from the appropriate directory. Bringing it all together, example workflow with pg_tileserve, recommended. This is the simplest and most direct approach. 1. Install PostgresQL, PostGIS, and pg_tileserve. 2. Create the database and enable PostGIS. 3. Import the OSM data using OSM2 PGSQL. 4. Add the OSM_ID column, if needed, and create indexes. 5. Simplify geometries by adding geometry_simple columns. 6. Create the SQL functions, get_roads, get_buildings, get_water, etc., for each layer. 7. Set the database_URL environment variable. 8. Run pg_tileserve. 9. Access the tiles through the pg_tileserve URLs or the built-in viewer. Example dockercompose.yml, optional, but recommended for reproducibility. To use this: 1. Save it as dockercompose.yml. 2. Run dockercompose upd. This will start the PostgreSQL and pg_tileserve containers. 3. Get the OSM data, example Germany latest.osm.pbf. 4. Connect to the PostgreSQL container, docker execute db_container_id psqlu osm_user d osm_data, replace db_container_id with the actual container id. 5. Run the create extension statements and the SQL queries to create the functions. 6. Run OSM2 PGSQL inside the PostgreSQL container. 7. Run the SQL to add indexes and simplify geometries inside the PostgreSQL container. 8. Access pg_tileserve at http://localhost 7800/. Troubleshooting. *slow queries * ensure you have indexes on your geometry columns. Use explain analyze to analyze query performance. *large tile sizes * simplify your geometries using st_simplify preserve topology. Check your data types. *errors with OSM2 PGSQL * double check the database connection parameters and the path to the style file. *PG_tileserve errors *verify the database_URL environment variable is correct. Check the PG_tileserve logs for errors. *missing data *ensure your SQL queries are correctly filtering and extracting the data. Key takeaways. Simplification is essential for vector tiles use st_simplify preserva topology. Indexes are crucial for query performance. Experiment with zoom level specific queries. PG_tileserve is a convenient option for serving tiles directly from PostGIS. Docker Compose simplifies setup and reproducibility. Understand the limitations of vector tiles. They are best suited for general purpose map display and not for complex spatial analysis. This detailed tutorial provides a comprehensive guide to processing OpenStreetMap data into vector tiles using Dane Springmeyer's techniques and tools. Remember to adapt the code and configurations to your specific needs and data. Good luck.